So let me pull up this derivation I did there. Here it's called water surface. Okay, so the question is, why does the image look closer when you look down into water compared to just straight in air? So what I've got is this is the water surface. This is the bottom of whatever we're looking at. So we'll assume we're looking at something on the bottom of the body of water, and there's a certain depth from the water surface down to the bottom we call D, and D sub A is the depth of the I don't know what A stands for, but that's the depth that we perceive the object to be. Because when we look in, our mind is thinking we're following a straight line. And so whereas what's really happening is the light is coming in and then it gets bent towards this normal. So the blue line is normal to the blue surface. And so we think that these two distances are the same. The distance from here to the left, well, from here to the right. If there was no water in here, that's how long we would perceive the object to be. Well, we're still using the same distance, but what we're doing here is we're assuming that it's going straight. So the angle that your eye would see going, what we're thinking, our brain is thinking, is equal to the angle that the initial light ray makes with the normal, theta 1. So this angle's theta 1 between blue and red, whereas theta 2 is the actual angle that the light bends through. So this would be my angle of incidence, this would be my angle of refraction. But here we're assuming it goes straight. So it's just a matter of doing geometry. The key thing is that we assume, because the angles are small, so because both angles, theta 1 and theta 2, are small, we can assume that the sine of the angle and the tangent of the angle is actually equal to the angle. So if you look at the graphs of sine theta, tangent theta, and just theta, on a graph, they all come together when you get close to theta equals 0. And this approximation is used a lot. If you look at the derivation of the thin lens equation, we presented the results, but that derivation is done assuming that the angle is equal to the sine of the angle, or the tangent of the angle. So if we look at these two triangles, this triangle, you've got this side of the triangle is the depth. This side of the triangle is this B distance horizontally. So the tangent of this angle theta 2 is going to be B over D. Whereas for where we're perceiving the light, where the object is, we use this triangle. So we have, instead of D, we have D sub A. We still have B. B is still the denominator. So well, actually in the numerator, B over, in this case, B over D sub A is the tangent of theta 1, and B over D is the tangent of theta 2. Also, Snell's law says that N1 times the sine of theta 1 equals N2 times the sine of theta 2, where these are the index of refraction of the two materials. So if we take the ratio, take this equation, both of these equations, and we say that the angle theta is equal to the tangent and the sine, we could say theta 2 over theta 1 is approximately equal to the tangent of theta 2 over theta 1. So we're using that approximation to go this way. And if you take the opposite over the adjacent, the opposite sides cancel out, and you end up with the perceived depth divided by the actual depth as being the ratio of the two angles. And you can then use the same kind of argument on Snell's law. So if you take this equation and find the ratio of theta 2 over theta 1, it's going to be equal to N1 over N2, but we're making the assumption for small angles that theta is equal to the sine of theta. So this is theta 2 over theta 1 is equal to that. Theta 2 over theta 1 is equal to that. This is from geometry. This is from Snell's law. What you end up with is n1 over n2 is equal to d sub a over d. Or the perceived depth is the actual depth times the ratio of the indexes of refraction. Well, n1 is air, so that's 1. And water has an index of refraction of around 1.33. So if we plug those numbers in to that equation, if I find my cursor, so those are the two values that we use, we see that the perceived depth of from the surface to the bottom is about 0.75. So if we were to try to grab that fish, say the water is this far, this deep, but we think it's this deep, so we would grab for something here, but the actual fish would be down there. So you've got you'd have to say, I'm not going to think of going where the fish is, I'm going to go through the fish and grab something below the fish to actually get to the right location. And it turns out that D would be equivalent to the object distance, and Q would be equal, this would be the image distance, which would be the distance we perceive. And these would be virtual images. What we're looking at in the water, the actual object is at say the bottom of the pool. We're seeing this virtual image that is closer to the surface than we think it is. Just like when you use a magnifying glass and you look at something behind the magnifying glass, you're not looking at the object, you're actually looking at the virtual image of that object, which is still still behind the lens, but in that case it's usually magnified. Here, I didn't actually mention whether it was magnified. I think it actually looks the same size because it's closer, but it's smaller. So I think we perceive it being the right size. It's just the depth, how far behind the surface that image is different. It turns out you can get, in the book they talk about using the thin lens equation, but letting the focal distance equal infinity, and ultimately you end up with the same result. But this is my attempt. This is what I did when I went back after physics, and I said I didn't know what to do, so I came up with this, and it agreed with the book. So I was happy that I actually did something right. So that was good. Okay. So that's it for right now. On Wednesday, what we'll do is the first hour before Bob comes is we'll talk about telescopes and microscopes and how and we'll pull out the kits and we'll make them. Okay, so we'll talk about how they work and then we'll make one and see how it works, and then we'll have our guest speaker, which I'm sure you all will be very interested in. Okay, so we're going to move on to, move back again. We're going to move to chapter 10. So this is thermal physics. I don't know why it's doing that. Let's try here. Open. Okay, that makes more sense. It's like, why isn't it giving me... Okay, these are the topics I mentioned the other day that we'll be covering in the next 3 chapters. One is talking about temperature. One is associated with something called heat capacity. Latent heat, that's where you change from one phase to another. So we'll talk about melting and boiling, condensation, how much energy you have to put into the substance to get it to change phase, and how much energy you have to put into the substance to increase the temperature during a given phase. So that's what's related here. Heat transfer is how do you take the temperature difference between two bodies or across a body and calculate how much energy is being transferred between those 2 points. In mechanical engineering, you spend about at least a semester doing heat transfer. You spend about a year doing thermodynamics. Thermodynamics is relating heat transfer and work to changes in properties of fluids and well, liquids and gases. That's the course that I taught when I was at Tech getting my doctorate. It was thermodynamics. Okay, so the first thing we're going to talk about is this thing called thermal equilibrium. And what that says, I didn't do a very good job writing, but two bodies in thermal equilibrium have the same temperature and there's no net energy transfer between the two bodies. So we've talked about equilibrium relative to forces. Force equilibrium says the sum of the forces equals 0. And when you have force equilibrium, you have no change in velocity. Normally it's 0 velocity. So we did those problems. We set sum of the forces equal to 0 in the x direction, sum of the forces equal to y in the y direction. We also did the sum of the moments was equal to 0. That's mechanical equilibrium. Thermal equilibrium is where you have two bodies and there's no exchange of energy between the two bodies due to heat transfer. Now, sometimes we perceive that two bodies have different temperatures, but they don't actually have different temperatures, which I have a video which I'll show you that's kind of interesting. So that's it's kind of the chicken and the egg kind of thing. Things are in thermal equilibrium if the temperatures are the same, or you can also say if the temperatures of two bodies are the same, then they're in thermal equilibrium. And we know, we have a general idea of what temperature is. We use thermometers to measure temperature. So let me just move on to the next topic. Yeah, so two bodies have the same temperature if they are in thermal equilibrium. So one way of checking the temperature would be actually to have two bodies, and if you know the temperature of one body, and you could put another body in contact with the first body, the second body in contact with the first body, and if there was no evidence of any energy transfer between the two bodies, then you could make the conclusion that they have the same temperature. If you put two bodies in contact with each other and you saw evidence that there was energy transfer between the two bodies, then you could conclude that the temperatures are not the same. So two bodies have the same temperature if they are in thermal equilibrium. And so there's kind of this, it's kind of like the math theorem. Is it the commutative property? I always forget what it's called. So what we could say is say we have three bodies here, A, B, and C, if we know that body A and body B have the same temperature, and body A and body C have the same temperature, then we can conclude that bodies A, B, and C have the same temperature. So that's like if A equals B and B equals C, then A equals C. So you can do the same thing with temperatures. And if you were to if these have the same temperature and they were to touch, then there would be no energy transfer. And if I let these two bodies touch and there was no energy transfer, well, it would have to be if the temperatures were the same. Okay, so how do we determine temperature scales? Well, we have some kind of standard that we're basing it upon. So in science, the Celsius scale is used a lot, and we, not arbitrarily, but we decide for a good reason that 0 degrees C is going to be the melting point of ice at standard pressure. So we can therefore have some way of measuring temperature, and we can standardize it by using this easily reproduced condition. Likewise, the boiling point of water, standard pressure is standard atmospheric pressure, 101,000 pascals. And so we decide that we're going to, for the Celsius scale, we're going to say the boiling point of water is 100 degrees C. And then points in between are linearly determined. Now, as far as the Fahrenheit scale, 0 degrees C turns out to be 32 degrees Fahrenheit, and the boiling point of water turns out to be 212 degrees Fahrenheit. At least those are even. They're not decimal numbers, which is kind of amazing. Well, that's not amazing. They probably figured that out at some point. But, how did they come up with the Fahrenheit scale? This makes a lot more sense. This SI system makes a lot more sense to have melting point be 0 and the boiling point be 100. And it turns out that 0 degrees Fahrenheit was about the coldest that they could make something reproducibly. So what you would do is you take ice. I think the way it was, you take ice and you would put salt in it. So it would be a salt water mixture, and you could get down to about 0 degrees Fahrenheit before it froze. So they just chose a different place to set 0 degrees. And it turns out that 100 degrees Fahrenheit is approximately body temperature. So they decided to set 100 at typical human body temperature. I think then ultimately they probably came in with a Celsius scale, which made more sense relating it to the properties of water. And then they probably adjusted these so that they weren't that far off from what they used to be, because our body temperature isn't exactly 100 degrees Fahrenheit. It's 98.6 on average. So, and as a consequence, you can convert between the two temperature scales. You've seen this before in chemistry, I'm sure. So if you have degrees C, you take 9, you multiply it by 9/5, add 32. So 0 degrees C is 32 degrees Fahrenheit. If you plug in 100 degrees C, you'll get 212. And you can go the other direction. So if you have Fahrenheit, you subtract 32, multiply by 5, divided by 9. And then we have these absolute temperature scales. So Kelvin is degrees C plus 273. And that was set because 0 Kelvin is absolute 0, which is as cold as you can get. So that's what the absolute 0 K is, the lowest temperature that you can reach using all kinds of weird ways to do that. So let me find this video, watch a little video here about perceived temperature. And so I'm going to open up YouTube here. Actually, what I'm going to do is do this. So we have Veritasium temperature. Yeah, that's the one I'm looking for. Change this to the speakers. Okay, turn this thing up.
Cold. When you touch an object object and it feels warm or cold, what is that really telling you about the object? Here I have a metal hard drive and a book. And I'm going to ask people to compare their temperatures. Which one do you think will feel warmer, the book or the hard drive?
The temperatures?
Yeah, tell me if one is hotter or colder, or if they're the same temperature. How do they feel?
This is slightly colder than this one.
Yeah. Oh, that's warmer. Yeah, way more.
Yeah, agreed.
I'd say the hard drive is a lot colder than the book. I don't know, because the book's got more knowledge.
Why do you think that is?
Metal's normally a little bit chillier if you leave it in a colder temperature.
Well, what if I said that they're both at the same temperature? What would you say?
So you're lying.
But really?
I think you're lying, yeah.
Oh, jeez. Well, maybe the way I could prove it is I have an infrared thermometer. What do you think we're going to see?
I think science might be able to answer that. And I'm not a scientist.
Make a prediction for me.
I still think that's cool though.
Would you bet me money?
I do because I don't have any cash. So,
Let's measure the temperature of the book.
Okay.
What do you see?
19.0.
Okay. We measure the temperature of that.
19.0. Alright, well now I believe you.
I'm trying to actually figure it out, trying to figure out why they would be the same temperature. They don't feel the same temperature though.
So why does that feel colder if they're basically the same temperature?
good on. You get an answer?
Well, I'm coming to you guys for answers.
We're creatives, not intellectuals.
Well, create an answer for me.
I'm not a scientist. Come on, you tell me.
Well, I'll try to answer that question with another little experiment. Here is an aluminium block and
Ooh, nice and cold.
a plastic block. How do their temperatures compare?
Completely different. Completely different.
Aluminium much colder.
Yeah.
Yeah?
This actually feels colder.
Let's take this to the next level. I'm going to put an ice cube on both plates. What are we going to see?
Well, I'm guessing it would stay solid on this one and melt on this one.
So it's going to melt on the plastic but stay solid on the aluminium.
Yes, but maybe I'm wrong.
That one will melt more quickly than on the aluminium block.
Yeah, I think so. I think they're colder.
Yeah, because it's cold.
Let's
And I
actually-
think they're going to go the same.
Alright, so we put an ice cube on each of those blocks.
Wow.
What are you seeing?
Well, it is melting a lot quicker on the aluminium.
I got it melting.
It's melting quicker than that one. Even though this is aluminium, that's plastic.
So which one felt colder?
That
This
one.
one.
How does that make any sense?
I have no idea.
Could aluminium be bad for the environment?
How would aluminium be bad for the environment?
Well, it's thawing out the ice a lot quicker, isn't it?
So you want the answer?
Yes, please, please.
It's about thermal conductivity, right? The rate at which heat is transferred from one object to another. So when you felt these blocks originally, I know this one felt a lot colder.
Yeah.
But you know from the other example we did that they must both be at the same temperature.
True.
Because they've both been outside for a while. We see that the aluminium block is melting the ice faster than the plastic block because it's conducting the heat to the ice cube faster.
Okay.
With the plastic block, it's a worse thermal conductor, so heat is being transferred less quickly to this ice block, and so it's staying ice.
Okay. I believe you.
Make sense?
Yes, definitely.
You know, in our first example, the hard drive felt colder even though it was at the same temperature roughly as the book. And that's because the aluminium conducts heat away from your hand faster than the book conducts heat away from your hand,
Sure, that seems logical.
which makes the hard drive feel colder
Colder, yeah.
and the book feel warmer.
Yes.
So when you touch something, you don't actually feel temperature. You feel the rate at which heat is conducted either towards or away from you. Think about this next time you hop out of the shower in winter. It's much nicer to stand on the bath mat than on the tile beside it. Not because the bath mat is warmer, but because it conducts heat less quickly away from you.
Got that? Yeah, so we can't use our physical perception always to determine whether something has a different temperature. He's basically saying that the aluminum, as we would say, that that it transfers energy from our warm hand to the colder block more quickly than from our warm hand to the cold plastic thing. And so our body is not measuring temperature, it's measuring how quickly energy is transferred from our body to somewhere else. Okay, and that's kind of the whole idea with wind chill. And the temperature is not any lower, but it's transferring energy from us more quickly, and so we feel colder because of the wind blowing. So he used an infrared thermometer. There's other different ways. This was just to describe how they came up with absolute zero. They took gases and they reduced the temperature, and as they reduced the temperature, the pressure also reduced. So this must have been at constant volume, I would guess. And as they plotted those points, they didn't get to absolute zero, but they extrapolated these data points, and they predicted that when you got to zero pressure, you would get to negative 273 degrees C. And so they decided to set that as absolute zero on the temperature scale, assuming it was behaving as an ideal gas at that point. Okay, so that's it for temperature right now. The next thing in this chapter is talking about how the temperature affects the physical properties of a material. And we talked about that relative to resistance. We said that as the temperature went up, typically the resistance of the electronic element went up. So in terms of the dimensions of an object, as usually, I don't know if there's any cases where it goes the other way, but typically when you heat something up, when you increase the temperature of an object, it gets longer, and when it cools down, it gets shorter. So we said that relating to musical instruments. So the actual relationship, it looks like this. So you start with some initial length L0 in meters. The final length is L. And so you take the temperature difference from the initial temperature to the final temperature, and you have this property called the coefficient of thermal expansion, or thermal expansion coefficient. It's kind of like the I forget exactly what it's called. It's probably thermal resistive coefficient when we did it with electronics. And typically T0 a lot of times is 0 degrees C, or maybe 25 degrees C. 25 degrees C is kind of normal room temperature. And it's just showing that the way it's set up is just a linear relationship. As long as you're not too far from this reference temperature or the initial temperature, it is a pretty linear relationship. If you get too far away, then alpha is sometimes a function of temperature. So it may, but in our case, the kind of temperature changes that we're going to look at, the relationship between length and temperature change is pretty linear. I don't know if there's anything else written down here. Let's see what it is. That's it. Okay. So here's an example. Let me just put a little screen over this so we don't go too fast. So it turns out for steel, the thermal expansion coefficient is 1.2 times 10 to the minus 5, 1 over degrees C. And the reason it's 1 over degrees C is if you look at the relationship, you take alpha times temperature, so the temperatures cancel out, and 1 is unitless. So you have a unitless 1 plus, when you multiply these things together, it doesn't have units. And you add those together and multiply by the length, and that gives you length. So unit-wise, it makes sense. That's what it should be. So the question is, we have a 3,000 meter long steel bridge, and initially it's at minus 10 degrees C. What is the length at 35 degrees C? Now, actually, so this T0, it could be reference temperature if we wanted to find how much the length increased relative to the reference temperature. If this alpha is constant within the temperature range that we're looking at, then really it's just final temperature minus initial temperature. So we don't have to go to 0 degrees C or 25 degrees. We could do that and say it gets this much shorter going to negative 10 and this much longer going to 35, but as long as alpha is constant, we can just say this is the final temperature and this is the initial temperature, even though alpha is usually at some specific temperature. So, okay. So it's as easy as it looks. All you have to do is take the length, L, that's your initial length, and multiply it by 1 plus alpha, which is given here, times 35 minus 10. And you don't have to worry about converting it to absolute temperature, because all we're talking about here is temperature difference. So whether you're measuring temperature difference in Kelvin or in C, you still get the same temperature difference. In some cases, temperature has to be an absolute value, like with calculating the speed of sound. It's the square root of the absolute temperature divided by 273. That's because there it's a ratio of temperatures. Here it's a difference of temperatures, so we don't have to convert it. So if you plug those numbers in, you get the new length is 3001.62 meters. So the length of the bridge increases by 1.62 meters, which is that big. Okay. So even though alpha is pretty small, we wouldn't normally be able to see that if we had just a little 3-inch long something or other, a nail or something that was made out of steel, and we tried to measure the difference in length between these two temperatures. We probably would have a hard time measuring it. But if you're dealing with a bridge that it's that long, then the final result can be significant. So if you look at bridges, especially long bridges, let me just show you a picture here. Go to Google. So we'll say the thermal expansion joints, bridges, and we will look at some images here. And you can actually, that bridge like over at 220 that goes over the railroad, you'll see those. It has a little sign that says motorcycles beware, because you could have trouble. So what they've got here is they built it so that as the bridge, in this case it's steel and concrete and asphalt, it's going to grow and expand and contract based upon the temperature. So what you would do is you probably have, this thing would possibly go all the way to there at the maximum temperature that you can imagine, and it would probably go to somewhere like that. You wouldn't want it to go too far. You'd have this place where motorcycle wheels could go in there and cause all kinds of trouble. So that's why they're there, is because over a sufficient span, the distance, the change in length can be significant. Just looking in the background, it looks like that's a fairly big span that they're looking at. Let's see if find some other ones here. Yep. So that's why they're there. Now this one, there they've just got a little piece of rubber. So it must not be a very big bridge. Okay. So that's all there is to talk about relating temperature change to the change in the length. Now we're going to talk about what's called specific heat. And specific heat is this quantity, C. So we use C for capacitance. We use it for thermal specific heat. And it fits into this equation. It's basically asking how much energy do I have to add to some mass of material to get it to increase a certain temperature. So Q is the quantity of energy transfer due to heat transfer. And that has units of joules. Remember, joules is also the unit of work, because they're equivalent to each other in some ways. If you take a paddle and you do 1 joule of work churning up that water, you should be able to see the fluid should increase proportionally to how much work is done on it. M is the mass in kilograms, C is the specific heat, has units of joules per kilogram degree C, and delta T is the change in temperature. And again, because it's the change in temperature, we can just use degrees C. We don't have to convert it to absolute temperature if we don't want to. It can be either one or the other, just as long as you're consistent. If you use Kelvin for both temperatures, then that's fine. So it's the final temperature minus the initial temperature. And so, the question is, what I guess it might be, why? What does it make any difference? Well, one thing is, if you're using some material to store energy from solar energy, you want to take the sun's energy, you want to store it somewhere, you would want a substance that has a high specific heat. Out here, so I'm tethered now. Okay. So here's a couple of materials, and you can see I've got water, but they have different specific heat depending upon which phase you're in. So ice has a specific heat of 2100 joules per kilogram Kelvin. Liquid water has a specific heat of 4190 joules per kilogram Kelvin, and steam is about 2000. So when you are ice, you're increasing the temperature of ice. For every degree centigrade or Kelvin per 1 kilogram of material, you have to put in 2100 joules to raise it 1 degree C or 1 degree Kelvin. For liquid water, you have to add more energy. And it all depends upon how the energy is stored in the molecule. As you increase the temperature, what mechanisms are there to store energy in terms of things like vibration or rotation? I don't know all the details of the different ways energy is stored. Now you look at something like copper, it only has a specific heat of about 390 joules per kilogram Kelvin. So it takes much less energy to raise a kilogram of copper 1 degree C than it does water. So that's steam, if you're wondering what that was. Liquid water, steam. So that's if they are, you can use this equation if you are changing the temperature within a given phase, within ice, within liquid water, within steam. If you are if you're taking the substance, you're changing the phase, and the phase change occurs at a fixed temperature. So if you have ice, it's going to melt at 32 degrees Fahrenheit, 0 degrees C, and it's going to have that same temperature when it's 99% solid and 1% liquid, or 99% liquid and 1% solid. It's going to have the same temperature. Okay, so here's an example. How much energy must I add to 2 kilograms of liquid water to raise the temperature by 25 degrees C? So we have our equation. Energy is equal to mass times specific heat times the change in temperature. So we just put 2 kilograms, use the specific heat for liquid water, 4190, multiply by the temperature change, 25. And I use Kelvin here, but because it's temperature change, it doesn't matter which units I use. I guess because the units here are Kelvin, but I wouldn't lose a lot of. You could probably interchangeably put degrees C or Kelvin in there. So you see it when you multiply those numbers together, you get 209,500 joules, which is 209.5 kilojoules, or 2.095 megajoules. So we do tend to use these kilo, mega, because to 2 kilograms, that's about 4 pounds. So it's not a huge amount of water. 25 degrees C is not a huge temperature difference. So in terms of joules, you can get some pretty big numbers when it comes to calculating the amount of energy. So to get from here to here, you divide by 1,000, to from here to here, you divide by 1,000 again. So that's pretty easy. Okay. Now, during the phase change, as I said, the temperature does not change. And we have two quantities. These are physical properties of the material. You have what's called latent heat of fusion. So L stands for latent heat, F stands for fusion. And that's either melting or freezing. So if you're putting energy in, you're melting it. If you're taking energy out, you're freezing it. But the process is fusion. So this is not latent heat of freezing, it's latent heat of fusion. And then you have L sub V, that's the latent heat of vaporization. So again, if you're adding energy, you're boiling. If you're taking energy away, you're condensing. And for water, these are pretty big numbers. So the latent heat of fusion is 334,000 joules per kilogram. And the latent heat of vaporization is 225,600 joules. No, actually that's million. 2,256,000 joules per kilogram. So you have to put a lot of energy into to change something from a liquid to a gas typically. I think that's 334, not 339. I'm not sure. I'll find out here in a second when I use it. So the kind of question that usually is asked is if you start at ice and you melt the ice, then heat the ice up, the water up to boiling point, boil the water, and even after it's boiled, you heat the steam up beyond its boiling point. How much total energy do I have to add to do that entire process? Because your first thing you're going to have to do is heat the ice up to freezing, then you melt it, then you heat the water up from 0 to 100, then you boil it, and then once it's boiled, you heat it up from 100 to whatever the final temperature is. So you just have to make sure you do it. And for the calculated the heat transfer, it's a little simpler when you're talking about boiling, or because there's no temperature involved. All you do is you take the latent heat of fusion times the mass. That'll give you the total energy added or subtracted depending upon which way you're going. And the same with boiling. If you want to know the energy to boil something, you multiply the mass times the latent heat of vaporization. And if you're somewhere in between, it's linear. If you wanted to melt half the ice, so it's half liquid and half solid, it would be half of the latent heat of fusion. If you melt 3/4 of the ice from a mass perspective, you do 3/4 of the latent heat of fusion. So it's okay. So here's let me put this on one screen. So how much energy is required? This is for 4 kilograms. So when I wrote this up, I forgot to tell you how much mass it was. How much energy is required to change ice at negative 15 degrees? So I'm going to cover that up. Change ice at negative 15 degrees C to steam at 140 degrees C. So the ice is below the freezing point and the steam is above the boiling point. So you've got 5 processes. You've got to heat the ice up to 0. You got to melt the ice. You got to heat it up, the water from 0 to 100. You got to boil the water, and then you've got to heat the steam up from 100 to 140. So let's just look at each one of those. Probably won't get all the way through. So the first thing is to raise the ice from negative 15 degrees C to 0 degrees C. So when you're dealing with just a single phase, you just use this equation. So the amount of energy is the mass times the specific heat of ice. The temperature change is plus 15 degrees C. So you plug those in. The specific heat of ice is 200. We have already done this. It's 2100 joules per kilogram Kelvin. So if you take 15 times this times 4 kilograms, you'll end up with 126,000 joules. So I don't know if I actually show the calculation here or not. Let me see. Can't remember if I did or not. Okay. So let me just write that out because I didn't show that. So all we're doing to get this number here is just 4 kilograms times 2100 joules per kilogram Kelvin times 15 degrees C. That gives you 126,000. Okay, so now once it's at 0 degrees C, you melt the ice. So there we use the phase change relationship. So the amount of energy is just the mass times the latent heat of fusion. So the latent heat of fusion, that still is not, I must have copied it from the previous page. We'll assume it's 334,000. So that times 4 gives you 1,336,000. So it takes almost 10 times as much energy, more than 10 times as much energy to melt ice than it does to raise it from -15 to 0. And it won't be this week, but it'll probably be next week. We do this experiment where I freeze a gallon of water and I stick it in a cooler, and we see how long it takes for the ice to melt inside the cooler. If you've ever been camping, a lot of times you'll take a gallon of water and you'll stick it in the freezer. And one question people have is, well, when do I have to worry about the food going bad? And as long as you see a little sliver of ice in the gallon of water, you're still going to be okay. Because as long as there's just a little bit of ice, the temperature of the water has to be 32 degrees Fahrenheit or 0 degrees C. But we'll actually demonstrate that. Okay, so next time what we'll do is we will continue on, do the 3 remaining parts, and actually next time we'll do some stuff with telescopes and microscopes, Mr. Donnan, and all that good stuff. So I've assigned, just so you know, remember you should be doing homework through chapter 23, right? So 22, 23 should be on your list of things to do. And the test is next Monday.